All right. Everyone hear me?
Yeah.
Okay. Welcome to my talk. Orko, where are we now? So I'll just quickly introduce myself. My name's Alex Benet. I'm the virtualization and emulation tech lead for Linaro. So just a quick overview of what I'm going to talk about. I'm going to give a quick review of what Project Orko is and its aims and what we're trying to do with it. Then I'm going to talk a little bit about how multimedia devices relate to VirtIO and some of the challenges that they introduce. I'm going to talk about some of the hardware challenges we've had whilst implementing this for the demo, and then give a sort of overview of the demo as we planned it and what you're actually going to see, and also give a bit of a vision of where we'd like to go. Okay, so first of all, Project Orko. So the aims of Project Orko are to provide safe and efficient VirtIO devices for hypervisor agnostic cloud native workloads. So there's a lot of buzzwords in that phrase. So let's just break that down a little bit. So first of all, VirtIO. So VirtIO is a hypervisor aware para-virtualized device specification. So it's an open specification defined by the folks at Oasis, and it's specifically designed to run on hypervisors with a device model that's designed to make sure that you have minimized the number of expensive guest exits you have to take into the hypervisor. Because although hypervisors try to be as efficient as possible, every time you exit into the hypervisor, that's several context switches. So the basic design involves having a device driver in your guest kernel. It's often referred to as a front end. This does transactions that are basically blocks of shared memory that are shared over these things called vert queues. You can have multiple vert queues for your device, and that's shared memory with what's happening in the back end. These are handled by a VirtIO transport, which is another abstraction that separates the device definition itself from how the hypervisor specific details are dealt with. So although all the transactions are done with shared memory, there's a number of things like notifications and configuration handling that have to be done in a hypervisor specific way. And then on the other side, you have your hypervisor interface that brings the notifications from the transport. You need something that deals with the configuration and control of setting up a VirtIO device. And then the backend itself basically spends its time processing buffers and filling in results, sending them back to the guest. Hypervisor agnostic. So VirtIO was originally very much a creation of Linux and KVM. That's the world that it comes from. And the implementations started up being very tied to the host and hypervisor that they're running on. So for example, if you're using the vhost kernel backends, they're quite intimately tied to the guts of Linux. So if you've got a vhost kernel network backend, it's injecting packets directly into the net buffers inside the kernel. We want to be hypervisor agnostic, so we have chosen the route of using vhost user, and these are backends that are implemented in user space. They're portable, so we can build them for any Linux-like OS, but we can run them with a number of different VMMs. QEMU's the common one that we use, but also cross-VM. And in the Zen case, you can run them standalone with a little program to manage the creation of them. And we abstract the hypervisor differences in the library level. So the drivers, the device implementations themselves are not aware of what hypervisor they're running on. They're just aware of the virtqueue messages coming in and out, and all the differences of how the hypervisors deal with sharing memory is abstracted away by the library. We've chosen Zen to demonstrate it just because it's not KVM, and also Zen has some interesting properties that make it useful for people that are interested in type 1 hypervisors, things like automotive and industrial applications, where you don't want to have a whole type 2 hypervisor and all the baggage that comes with combining your hypervisor with your kernel. Cloud native is another good buzzword. So cloud native is basically the idea that you can develop and test in the cloud and then take your tested workloads and deploy them on the edge. So this is one of the things that is called for by the SOFI architecture. And to do that, you need strong abstractions. You don't necessarily have exactly the same underlying hardware in your cloud that you do on the edge device, but the whole point of having a VirtIO abstraction there is it doesn't matter to the workload itself. Safe and efficient. So the original VirtIO design was very much based on the Linux KVM model, as I mentioned before. You have untrusted guests. You're dealing with quite a lot of guest data, so there is a potential for memory safety errors. And the device backend running in the host domain sees everything about the guests. Okay, you basically have to trust it for everything. The Orko backends we've implemented them under Rust, under the Rust VMM project. So that's to deal with the fact that you're dealing with a lot of untrusted guest data. Rust allows you to work with a little bit more certainty about the safety of not making the sort of mistakes you can in C. And also, we've been working with stricter memory models. So Zen offers a thing called grant memory. And the idea there is every time you do a transaction, the guest explicitly grants access to just the memory needed for the transaction to the host to do what it needs to do. The host doesn't have complete access to the guest's memory. So just a little bit more about Rust VMM. So Rust VMM is a relatively new project. It was created in December 2018. So it builds on the work of Google's CrossVM and Amazon's Firecracker, which were both implementing VMMs using Rust as the implementation language. And they very quickly realized there's an awful lot of commonality in this, and they created the Rust VMM project as a place to put all the components that you need to build VMMs. So it's very much a sort of toolbox kit of things you can use to build a VMM. Obviously, there is a VMM reference, which is a relatively toy VMM, but uses the Rust VMM components to build stuff. Other examples include Cloud Hypervisor, which is a big hyperscale VMM. And there's also various other interesting projects that use the Rust VMM components like libkrun, stuff like that. So the vhost device repository is part of the Rust VMM project, and that is a repository of VirtIO device backends. So currently, now in production, we have GPIO, I2C, VirtIO input, random number generator, SCMI, which is a management interface for ARM, SCSI, sound, and VSOC, which is a generic Unix socket transport that operates over VirtIO. Because we don't like to put stuff into production until it's been properly ratified and in the Oasis spec, we also created a staging area. So in the staging area, for example, we have VirtIO Video, which is, gives people the ability to try out the backends on their development systems without having to wait until the spec is ratified. And currently in flight, there's pull requests to add VirtIO console, VirtIO CAN, so that's the CAN bus, which you often see in automotive, and SPI, so they're all coming soon. The vhost device repository is maintained by maintainers from both Linaro and Red Hat, who also have an interest in this. So this is just a diagrammatic overview of what a typical Orko deployment looks like on Zen. So we have your DOMU, which is your guest, with its driver and its vert queues. You have the hypervisor, in this case Zen, and we have a tool called the Zen vhost frontend. So this basically takes the place of a VMM. So in the Zen world, you don't have a full VMM, you have the Excel tools that create and destroy guests. And then the Zen vhost frontend is responsible for the initial configuration, discovery of VirtIO devices and setting things up, communicating over this vhost user interface to the actual backend itself. And that's the same communication that CrossVM would use or that Qemu would use. We've made a few changes. So for example, we've added support for the grant device for memory sharing, which I've highlighted there. And another little optimization that we've done is instead of using Zen's default IO rec mechanism, which is how they do their trap and emulate device emulation, we've implemented the event FD mechanism, which is a asynchronous way of doing the notifications. Because IO rec was designed very much for doing generic device emulation. The notifications in VirtIO aren't tied to a particular event. They're there just to kick things off so you can do them asynchronously. Okay, let's talk a little bit about what media devices in VirtIO, what challenges they bring. So the principal ones, higher throughput. So MP3, for example, if you remember those, 128 to 320 kilobits a second. But the VirtIO sound device doesn't work in compressed audio, it works in raw wave data. So you're starting to up the amount of data that you're pushing through. So that's like 1.4 megabits. Compressed video can go even higher. If you're using a 4K UHD stream, that can go up to 68 megabits of data. And by the time you get to GPUs, AAA games will do their best to saturate a PCI bus, swapping in as much high data texture as they can for each individual view between each individual frame. So the amount of data going back and forth between the guest and the host is potentially quite high. So that results in quite tight latency requirements. IRQ latency can get in the way. You don't want to be doing too many exits as you're queuing all this data up. Zero copy is very much sought after. You want to copy the data out once into a buffer. You don't want to be copying it between each stage, between your guest and the hypervisor and wherever you're doing your host. So this is just an example of some of the pitfalls that you can run into. So this is VirtIO sound. So as you're doing playback, you fill a buffer, you send it off to the hypervisor plays it back. But in an effort to try and reduce the amount of latency, the original VirtIO sound driver took advantage of what happened to be an implementation detail at the time. It would start filling a buffer, queue it to the VirtQ, and then continue filling the buffer on the assumption that the back end wouldn't get to the end before it did. But of course that breaks an assumption which wasn't particularly clear in the spec, and as soon as you copy that buffer in your back end, you end up with corrupted data. So one of the things we've done is made these sort of bear traps explicitly clear in the specification. VirtIO does provide a mechanism if you want to do this sort of low latency stuff. It does have a mechanism for doing permanently shared blocks of memory, which you could use for these sort of streaming type setups. Obviously, then you still need some messages to coordinate to make sure that the back end doesn't get ahead of the front end. But that's not what the driver was doing in this case. So, shared memory. I'll talk a bit more about that. So traditionally, all the memory in VirtIO devices has been managed by the guest. The guest will do the allocations, that will get mapped and shared into wherever the back end is, and then the back end will deal with that memory and pass it out. However, that's not actually enough for some of the use cases. For example, for a GPU, you might not be able to use a memory in any arbitrary place in your physical address space. You need it to be, for example, in the GPU's VRAM. There may be additional host requirements required by the back end. So you might need to have, for example, textures aligned to a particular boundary. So in the case of something like GPUs, what you actually do is you have a mechanism for allocating these shared buffers, but asking the host to do the allocate, or potentially asking the host to do the allocation for you. So in my slightly scrappy diagram, I'm trying to show this here. We have the GPU with a bunch of VRAM. A region of that GPU is reserved for the guest, and allocations for textures are done there. But you also might have allocations in the host system memory. For example, the command buffer might be allocated there for your Vulkan stuff. But all of this is then presented to the guest in the PCI bar region of the guest. And this sort of mapping adds an additional degree of complexity that you don't get with traditional VirtIO devices. And of course, each hypervisor has its own APIs for sharing this sort of memory between guests. Another challenge that we've come across is the way that hypervisor page tables are managed. So in a type 2 hypervisor like KVM, obviously KVM has complete control of the system. It's able to make sure that stage 1 mappings done in EL1 and stage 2 mappings done at EL2 are all consistent and in sync. But in a type 1 hypervisor, they're very much handled by separate domains. So the hypervisor handles stage 2, and the kernel handles the stage 1. And you have to take care with that. There is an additional complexity. It's not a simple case of adding all the attributes together. Depending on what you're doing, the device attributes with the strictest memory type would win, whether it's defined in stage 1 or stage 2. But those rules can be reversed when you're dealing with things like read and write permissions. Okay, so just a few notes about the journey we've taken onto doing this demo. PCI implementations. This seems to be a very hard thing to do. We've run into problems on the platform that we're using with the way that it deals with PCI device memory. So there are subtle differences between the way that x86 deals with mapped bar regions and the way that ARM deals with it. Technically on ARM, we're dealing with device memory non-cacheable. And we've also run into problems with write combining into that memory. So write combining obviously happens quite frequently when you're writing large amounts of data into the PCI space. And you need workarounds, quirk handling in the host kernel to trap when that data is unaligned and then to fix it up. Unfortunately, that means you also need the same workarounds in the guest to make sure that the guest can deal with that when it encounters that problem. We're also working with quite a lot of bleeding edge software. So the VirtIO GPU implementation for the Venus, which is the Vulkan device, has only recently gone into Mesa. So version 24 of Mesa is the most recent version. VirtIO sound went into 8.2 of QEMU, which was the last release of last year. The graphics stream stuff has been going in. I think most of it's in 9.0, but there's a few bits and pieces and bug fixes coming on. The kernel, most of the support in the kernel is already there, although obviously we've had to put local patches in. And then we're using things like the cross-VM graphics stream libraries. That's all under active development in Google's cross-VM repositories. The other thing to mention about VirtIO GPU is there are a lot of different approaches being explored right now. So the original VirtIO GPU was called Virtual Renderer, so that's an OpenGL-based approach. And that works reasonably well, but the performance isn't stellar. And the main reason being is OpenGL works at a relatively high level. So you do all your scene generation in your guest, then you send that all across to the back end for rendering, and there's a whole bunch of additional code generation and working out how to put that onto the actual GPU. And that introduces latency, so that affects the overall performance. That's one of the reasons we've been looking at Vulkan. Vulkan is a much lower level API into GPUs and is more suited to sort of a continuous streaming model where you don't have explicit sync points for dealing with when frames need to be displayed. But those aren't the only two. So Google have a project called Rutabaga, which is a general purpose encapsulation library. And that deals with encoding all sorts of different graphic streams. So for one example, they use it in Chromos to run Wayland guests and pass a Wayland socket through graphic stream so you can render windows in the host context. And finally, I should mention native context is another approach. So native context does use the VirtIO machinery, but it uses it in a way to do a similar sort of thing to a full-fledged SR IOV type setup where you expose chunks of the device memory up into a guest, but the guest, importantly, has to be aware of the type of GPU that it's talking to. So this is potentially one of the most efficient ways of doing it. It's not something that we're looking at directly because it doesn't meet our requirements for a strong abstraction for cloud native. Okay, so just what you can expect when you come upstairs on Demo Friday and have a look at what we're demoing. I will put this up first. This was our original plan. So what we wanted to have is we'll have the host running a number of vhost user daemons, including vhost sound and the graphics backend, running Android Auto guest. One of the things I want to point out, the VirtIO Venus device driver is implemented in Mesa. The Android graphics stack, although it is moving to Vulkan, doesn't use Mesa natively, so it's a bit of a cut and shunt to put the Mesa drivers into your Android image. I'm sure this will come eventually in the end. And we also wanted to show VirtIO operating between the main domain and a real-time domain. Unfortunately, we didn't get that part finished in time for the demo, but this is trying to demonstrate how VirtIO can be used as a generic glue to link together various systems. This is probably not the sort of setup you'd see on real devices. What you'd probably see is your low latency device running on a separate cluster, but you just need shared memory to expose that as a VirtIO device. So this is a much simplified thing is what you're going to see today, which is the VirtIO Venus device rendering some nice pretty cubes and Wayland benchmarks with QEMU as the back end. We are going to get to the full thing later, but you know, time pressures was amongst us. And finally, just to give a bit of the vision of the future, one of the arguments the native context people make is the GPU stack is a quite complex beast. You're doing quite a lot of user processing of all this untrusted data, and the argument the native context folks make is if you put that all in the guest, then at least if there's a problem, it's only the guest that gets is compromised. But in the Zen setup, there is no particular reason why you have to have your GPU backend in your main DOM0 domain. And you can move it all into a driver domain. So you put your backend for the GPU and the rendering in a separate domain that only has access to the GPU. So if it ever gets compromised, it can't compromise the rest of your system. All right. With that quick overview of the demo, we've got 2 minutes left if anyone wants to ask any questions. Yes, have you microphone?
So great work. This looks really exciting. Can you explain how you're validating this? Are you doing it on just virtual instances, or do you actually have this on hardware and testing it?
Yeah. So we've got a Ampere Altera Ava platform upstairs. Okay. So it's running an AMD Radeon GPU card in the host, and then running the virtual machines as virtual guests with this Venus GPU.
Are you guys doing automated tests on that machine as well?
Not yet. No,
okay.
No. We're still very much on the bring up phase.
Hi Alex, I had a question on this exposing the guest memory strictly whatever is needed, right?
Yeah.
Every transaction you would open up the strictly needed part of the guest memory.
Yes.
So that involves some overhead of page table manipulation and all that. So I was wondering if you have measured the cost of it.
So for the lower bandwidth devices, it's relatively negligible in the noise in terms of setting stuff up. But that's why for VirtIO GPU, most of the buffers are in these pre-shared regions. So yes, you don't want to be mapping and unmapping a whole texture buffer every time it's being updated. You allocate the shared region, and then that shared region is just used for the graphics data.
Yeah, because I'm told that any modifications in the stage 2 is very expensive.
Yeah, it can be.
It'll nuke the whole TLB, and that's why I'm interested to understand how much might be the overhead in practice.
Yeah.
Okay. And eventually, what all VirtIO devices you plan to develop backends for? I mean,
so I think we've done most of the low-hanging fruit now for VirtIO. I think with getting GPU to more production quality, that gives what people need for a general multimedia experience. I think the next ones, so the ones that keep getting mentioned to me, VirtIO camera and maybe VirtIO NPU for machine learning acceleration. The problems with VirtIO camera is just it's a very big problem space. So you have people wanting to have cameras all the way from stuff stuck on a car, monitoring for pedestrians, all the way to your latest Android device that needs to, do 10,000 shot modes and IP processing and all that sort of stuff. So I think we need to find a tractable part of that we can start the implementation and conversation with the community on. And NPUs are even further down. I mean, there's a lot of NPU architectures out there. So I think we're going to have to wait a bit of time to see that settle down and work out what a good common abstraction is going to be for that.
Yep. Great presentation, Alex. I was thinking, as a follow-up question about the problem with sharing only small regions of memory. Are you using VirtIO IOMMU for coordinating those regions, or?
So at the moment we use the grant table and foreign memory APIs in Zen, but people have talked about using an abstraction of an IOMMU in the guest, so it can program that virtual IOMMU, and then that gets translated to the actual mappings.
And have you evaluated the difference, the performance difference between sharing a small regions and using a shared bounce buffer strategy, which using the soft IO TLB that's in the kernel already?
No, not as yet. So the IOTLB, the bounce buffer SWI2 is useful for the low bandwidth stuff where you're not really going to notice the cost of copying. I think when you're starting to deal with these high amounts of bandwidth, you just basically want to avoid that like the plague, so you can have zero copy effectively.
Yeah, but it's only for the BQ contents.
Yeah, for things like texture, it's all the stuff that's going to be changing very quickly.
And one last thing, which VirtIO GPU implementation are you using right now?
It's VirtIO Venus. Venus is the abstract device which builds on the VirtIO GPU.
Yeah, but the device is, you are using the implementation in QEMU or a because user implementation of the GPU device?
So it's there's actually, so the driver is in Mesa on the guest, and on the host side, it's QEMU, which launches a thing called Virtual Renderer, which was also developed for Virgil, and then has the Vulkan backend in it as well.
But you're using the device that is all in the QEMU, in the in-process model. So
it's actually spawned into a separate process. QEMU spawns the Virtual Renderer as a separate process, but part of it's.
Okay. We are working on a because user GPU implementation in Rust, so perhaps we can sync up later.
That's something we might look at too in the future, yeah. Because there is a vhost user GPU implementation, but we've not really used that.
Thank you.
I think I'm way over time, so thank you all very much, and thank you.